boards to see if you actually understand MBT. MBT says two things must be true. A function f must be continuous and differentiable. Continuous from endpoint to endpoint. Differentiable, smooth turns everywhere in between. And if that's true, then, now technically there's a forever card. I'm just reading this little part. The forever card then, so this is all what we call the hypothesis, the conditions that must be met. If this and if this, then what can we say? There is a number C, at least one, guaranteed between A and B, such that f prime of C is equal to f of B minus f of A all over B minus A. What can we say? We can say that also there's a place where the instantaneous rate is the average rate. We can also say there's a place, at least one place, where the tangent is parallel to the secant. And we kind of got that written down before break. Then we did the pumpkin farmer. So what does that mean mathematically? Once again, if you have from endpoint to endpoint a continuous function, whatever that average rate is, for the pumpkin farmer, do you remember what his average rate was? He went the 5 miles in what? How many minutes? 4 minutes? What was his average rate?
7.
Okay, if the posted speed limit was what again? 55 miles per hour. He's speeding. How do you know? Motion is continuous. It's also differentiable. There's no abrupt changes. Well, there could be if he crashed. But anyway, in nice motion, his truck was fine. His jalopy, isn't that what they call it? Was fine. If his average rate is 75, just logically, we know he had to go faster. But in math, logic sometimes fails.
What?
Go to CalcAB and what we're doing next semester. It's going to fail sometimes. Because, wait. You want to do a life lesson real fast?
Yes. Yeah.
When would your logic fail you? Just think in life.
When
your intuition. When would your intuition, your gut, your logic, when would it fail you? Don't just say you're wrong. Think about what must be happening for your logic to be wrong, your gut instinct to be wrong, your intuition to be wrong.
You must be.
Maybe emotions are skewing it. That's one way, right? Emotions could be skewing it. Or things like, have you ever heard, don't make important decisions when you're hungry? Don't make important decisions when you're emotional. Don't make important decisions when you're tired. Why? Don't have big conversations when you're hungry. Don't have big conversations. Why? Because your logic is skewed, right? Because your emotions are kind of winning. Any of you guys get angry?
Yeah.
You're probably, it's not the best time to go and confront somebody. That's probably going to end poorly. Okay, so anyway, emotions or other outside factors could be affecting you to where you're not at your best. But let's say you are at your best. You've had coffee, you've had breakfast. It's a beautiful day outside. When could your logic, your intuition, your gut still fail you?
In perspective.
Perspective, possibly?
Overconfidence.
Maybe. I would say all of this might come back to how informed you are. Right?
That was big brain, Josh.
If one of you, right, but it's right, your perspective, your knowledge, your experience, all of this is kind of like how informed your logic is. Or isn't. Right? So could you guys be having a beautiful morning, walk into an operating room and say, let's go? You could, but would that surgery go well?
Absolutely.
Absolutely not.
Agree.
Right? You can feel great, but you haven't had the years of training or the experience or the informed perspective that hopefully surgeons have. Right? Okay. P.S. I was saying this is somewhat of a life lesson. Some of you get it, some of you don't. Can we just all admit that even up until the day we die, we will not have all the information that we need to have an opinion on absolutely every single conversation, every single argument, every single, we are limited, and that should bring not pride, but what?
Humility.
Humility. Not humility in an unempowered way, but humility in a there's always more work to be done way. Right? You could take the completely proud and ignorant approach. You could take the completely humble and weak approach. Or you could take the humbly informed and working to become more informed approach. If you go too far one way, it's dangerous. If you go too far the other way, it could be dangerous. There's supposed to be this blend of both to where we are humbly empowered when we take the right approach to any issue. Anyway, Jesus, help us all.
Amen.
Come back. Come back. But if as I was talking, you're like, ooh, I tend to be too proud, doesn't that mean you have to swing a little this way? Or, ooh, I tend to always act too weak, don't you need to swing a little bit this way? And rarely, rarely, rarely is any of this work or improvement or strengthening of perspective, information, knowledge, experience done alone. That's why one of the most marketable job skills out there is the ability to collaborate. Anyway, come back. Literally, one of the things all bosses want to see when they're interviewing you is whether or not you can be a team player. That doesn't mean that you're weak. That means that you are willing to and wanting to grow and learn from the people around you. Okay, what does this mean? The average rate. Remember the jalopy? He went 75? Now, was he doing this? No, I bet he was just like, and then he's like, and then, right? And he slowed down in time for the second cop. Like, he was not doing this. But the idea still exists. If his average rate was 75, which would be the slope of the secant line, the slope between the two beginning points, which is exactly what we found with the rise over the run, the change in distance over the change in time with a little dimensional analysis to make it make sense. His instantaneous rate would have had to have been, his slope of his tangent line would have had to have been 75 at least once. This graph says, ooh, I have 4 different places. Well, good for you, but MVT guarantees at least one time will the instantaneous rate be the average rate. You could also make an argument about this because of IVT. Ooh, help, help, help. IVT. Intermediate value theorem. All the in-betweens are guaranteed, right? If his average rate is 75 and he started at 50 and ended at 55, question, did he have to increase somewhere in that interval? Did he have to speed up somewhere to make that average of 75? Yes. He had to increase at some point. Did he have to also decrease at some point?
Yes.
Yes. So if we were to do 50 minus 75, to think about like his initial and his average, that would be a negative, and then 75 minus 55, that would be a positive. Basically, there's a 0 guarantee. There's a time when his speed minus the average would be 0. That's technically IVT. It goes a little deeper into the concept. You kind of have to make this whole other function about his current speed and his average speed. But if he starts at 50, 50 minus 75 is negative, so he has to gain speed to get up to that. 75 minus 55 is a positive, so then he has to slow down to get to there. IVT would say there must be a time where you hit 75. Okay, anyway. So what does this mean when you get to the math? And that's what you were missing, and that's what you didn't have a video about. Unless you did the watch it in homework. So, can you guys tell me once again, what's the big formula for MVT? What's the big formula for MVT? I'm going to write the if F is continuous. I'm going to write the other if, because there are 2 of them. If F is, what's the other one?
Differentiable.
Differentiable, which means the derivative exists on everywhere between. Then, tell me what comes next. Then what?
F prime of C.
There exists, Nazi math symbol, there exists a C within A to B, such that, this is me being lazy but also efficient with math notation. There must be, there does exist, at least one C in between A to B such that, now go, F prime of C equals what?
F of B minus F of A.
Over D minus A.
So when you're solving these, what should you have been doing? You should have been saying, is this continuous? Why am I going to automatically say yes, of course? It's a polynomial. Polynomials are smooth and they go forever. No denominators, no square roots, no ln's, no tangents, he's fine. What about this one? Why am I going to say he's not continuous?
He has a
It has an F.
And x, ooh, nice, because it's non-removable. since x cannot be 0. 0 is in between -1 to 2. The issue is in between. Think an asymptote, isn't it going to go forever high, forever low? It doesn't have to smoothly transition. So MBT is off. So this one, MBT does not apply. Ooh, that's nice. Is that possible? Yeah. I don't know what WebAssign would say. We can go look at it in a second. But basically, there are times where it's like MBT does not apply. I can't guarantee anything because the conditions aren't met. There's a life lesson in there somewhere too, but we're just going to come back to this one. Number 1. Continuous. Check. Why am I also going to say differentiable? And technically, I can say on all real numbers, which means that's good and that's good. Why are polynomials always continuous and always differentiable? Continuous, no denominators, no square roots, no ln's, no trig with asymptotes. We already said that, but why can I also say differentiable? How do polynomials always behave? Whether it's a parabola, or whether it's a cubic, or whether it's one of those weird with lots of terms quartics? What's true? No sharp turns. Always smooth turns only. And I told you that in pre-cal. You wrote it down. Polynomials, only smooth turns. What does that mean? Differentiable. Perfect. So what can we say? There is a place where, hey, what should we put in the f prime of c spot? For this function. No. In the f prime of c spot, what should we put for this function? So we're going to find f prime of x. What else do we need to find? What's on the other side? We need f of a, I need f of b, I need b, I need a, right? So let's go one at a time. I need my derivative. So to find my derivative, ready, set, go. Come on.
3x squared.
Keep going.
1 plus 1.
And then the minus 4 is a 0, right? Cool. Now we need to go for the average rate. Average rate. How are we at plugging in numbers? Can I assume we can do this? I hope so. If you need to, go out to the side and plug in f of b. Isn't that f of 2?
Yeah.
I'm just going to go slow and steady, which would be 2 cubed plus 2 minus 4, just in case you need it. I'm plugging in 2, right?
Yep.
Minus f of a. What am I plugging in? F of b is f of 2, plug in 2. F of a is f of -1, plug it in, right? How we doing? B is 2. A is -1. You can do this separately. You can do this all together. If you want to make a f of 2, let's go. Cool. F of -1, let's go. Cool. What did I do? I did the whole shabam all at once. Pause. Ask now. Do you see that I plugged in?
Yes.
I plugged in 2. Why? Because I was doing f of b.
Yes.
I was doing f of b, f of 2. Plug it in, minus. Then I did f of a, f of a, f of -1. Plug it in, simplify. What do I get? Come on, PEMDAS.
14.
8 plus 2 is 10. 10 minus 4 is 6. Minus -1 cubed is -1 minus 1. -2. -2 minus 4. -6. Remember, you're negative on the number line and subtraction says keep going more negative. So -1 minus 1, -2 minus 4, -6. Cool. Minus -6. Ooh, what does that mean?
12.
We need it here. Minus a negative is a plus. That's going to be 3. And 6 minus -6 is going to be
4.
12.
yeah, 12 over 3 is. So what am I going to actually be doing here? I'm going to be setting 3x squared plus 1 equal to, wait a minute, isn't it supposed to be f prime of what? F prime of c.
Really?
So I just take my f prime, I throw a c in it, and I'd be like, let's go find the special c. Let's go find where the tangent is the secant, where the instantaneous is the average. Oh, hey, set it equal to the average. And the average is 4. At this point, you guys should be able to see the name of the game. The name of the game is find any c's guaranteed by the theorem. Oh! So can I do 4 minus 1 is 3? 3 divided by 3 is 1. c squared is equal to 1, so therefore c is equal to plus or minus 1, but then I'm going to go ahead and say what's in between. Wait a minute. What does MVT say? Is it closed or open? I'm looking for all the places in between. So am I going to take both of those and say they both are? What's in between negative 1 to 2?
Yes.
Only
1.
1. Dun, 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 dun. Ah, the crowd goes home. This has kind of everything. It has somebody that fails, so we can't say anything. It has somebody that passes, and so we go for it with the derivative, with the average, setting them equal, and saying, let's go. It has us getting 2 different C's, 2 different places where the tangent is parallel. But wait a minute, if this thing is only going from 11 p.m. to 2 a.m., what? I'm thinking an hour before midnight, 2 hours after midnight. That's one way of thinking about it. If it's only traveling between those 2 times, I only care about what's happening in between.
Oh.
The theorem says, look at it. A C, I know, snazzy E backwards means there exists. Okay, some of you are still just looking at that backwards E. There exists. Remember, mathematicians don't like writing tons of words if we can avoid it. This one would mean for all. You guys already know this little guy means within. Anyway, math vocab, have fun.
$200 I have extra.
Oh my god.
What's good?
There are more examples on the video that is, sorry, Hovan, now attached to section 3.2. There are now examples on the video that is now attached to section 3.2. That is now attached to section 3.2. We're going to go ahead and tackle, now pause, look at 81, 82, and 83 again. 81 is having us think about what?
I don't know. Piecewise.
False.
A piecewise function,
That's horrible.
whether they're smoothly connected, whether it always exists, and the limits exist. This would be a plugging in, and a plugging in, and seeing if that's true or false. This is all to do with conditions. This is all to do with conditions. Checking all the ifs of a weird function. What's this one having to do? Oh my goodness, isn't it super similar to what we just did, just with kind of a few different numbers? Sweet! How about this one? Which of them would fail the ifs? So we have the ifs, then we have a solvable one, and then we have a which ones would fail the ifs down there. The groups up to the board are, I would say the same as last time, but Rocco wasn't here, was he? So let's go ahead and... Regular groups? I don't remember what the regular groups were, though. Huh. Oh, sorry, yeah. All of them only have one answer. Great question. All of them only have one answer. Three, and 4. 3, and 3. Okay, 3 guys on the side. 4 right here, so Lucas and Josh and Hez and Danielle. And then 3 and 3, we can do Sarah, Andy, and... Is that what we did last time? Back 3, front 3? Yeah, back 3, front 3. Go!
You're afraid.
Josh, Isaac, Ryan, Rocco, you're in the front.
I didn't even say it like that.
Fuzzy and team. Just the first person that I saw. Straight back. Sarah and team, straight back. You guys, yeah, erase. Let's start with number 82. Any questions? Oh, sorry, 81. Who wrote on top of my 81?
Oh, hey.
Oh, it was.
It was so pretty before.
Yeah, Hezzy, come on, man.
Can't say please copy your recent.
No.
It's like halfway through
Oh, never mind, it's all better. Okay.
Then disappears.
Any questions on 81? Why is it C? First of all, why is it this graph? You can't always graph it, but this one you can. Isn't this an mx plus b?
Yeah.
Except they did it backwards because they don't like this like negative in front. They'd rather have a minus. Okay, fine, whatever. But this is a slope of -1 and a y-intercept of 1. The line says I'm going to 1. The point says I'm at 0. The approach and the at, they don't agree. Remember your fold out? Or your foldable with the definition of continuous? 3 things have to be true. The function is there. Yay, it's at 0. The approach has to exist. Yay, it's headed to 1. But is the headed to 1 equal to the 0?
No.
No, so the function is not continuous. The function is not continuous, which I kind of showed in the definition. I didn't show in words, but the at is not the approach, therefore no. Is that okay? Function is not continuous. P.S., hold on. The derivative of the top is 0. The derivative of the bottom is -1. Why did the differentiable clue work? The derivative of 0 is 0. The derivative of 1 minus x is -1. The derivatives do not agree. The derivative does not exist where? Where does the derivative not exist? Look, I see slope, I see slope, I see slope. All of these are good. The slope is -1, -1, -1, -1. Where does the slope not exist? At 0. This one says I'm going to a slope of 1. This one says I have a slope of 0. Do the derivatives exist? No. But what does the differentiable clue say? Not closed, but open. Why is that different? As you said this earlier. What does it mean if it's only open? It says only look
In between.
in between. Only look in between. Are there slopes in between the endpoints? Are there slopes in between the endpoints?
Oh, yeah.
Right, does that make sense?
Yeah.
Why am I bringing up that big idea? What did you have to understand for this whole problem?
Okay. Can I argue my case?
Pause. Pause. Can I ask about the in-between? MVT says you're only needing differentiability between the endpoints. Continuous says from endpoint to endpoint. Differentiable says in between. And that was the exact illustration that we had a second ago. As far as
I can't relate.
right here. This will still be true. MVT will still be guaranteed if this graph were to have this on the other side. But it's not differentiable, it's a sharp point. But I don't care about the endpoint being a sharp point. I care about everything in between needing to be smoothly turning. Number 83 said you need differentiability in between. I don't care about the endpoints. And that's why MVT expressly says, which you guys aren't going to like as far as memorizing, but continuous is from endpoint to endpoint. It has to have points. If it doesn't have points at the endpoints, then I can't have a secant line. I have to have a point there, and I have to have a point there to even have an average rate. So from endpoint to endpoint, I have to have continuity. But differentiability only needs to happen in between. Now we can still talk about 83. But actually, this whole in-between idea was crucial for 81 and 83. Because 81, the derivatives do not agree at 0. But I do not care about 0 because my differentiability is only in between. Before we go to 83, 82. How were we on actually solving an MVT problem? That was the example at the beginning of class. Give me a thumbs up if you're like, no, I can do this. Does that make sense? But can you find a derivative? Can you find an average rate? And can you set them equal and so on? Why was it not plus and? Well, they didn't even give you an option for negative, did they? I don't think they gave you a multiple choice for a negative. Weren't they all positive? Okay. But do you guys see why it wasn't plus or minus? I'm only looking between 0 and 2. So I would only take the positive one between 0 and 2. I cancel out this other one. But still, they just rationalized it, right? Multiply top and bottom by a square root of 3. Okay. All right, go ahead. I'm all ears.
Okay. So I thought since it was in the closed bracket. For C,
Which one? Continuous?
Something.
Good question. For all of them, they were talking about the interval -1 to 1 because MBT is talking about on an interval, a closed interval A to B.
Okay.
So MBT is talking about a certain portion of a graph, but differentiability by the definition and the guarantee by the definition of MBT, the theorem itself says only look in between. But I see what you said. So you saw the question, saw that it was closed, and thought that that trumped. Like that went above and beyond, not as in trump at all.
And I did the math.
The past president. So knowing that MBT, the theorem itself is what is to be focused on. Now, do we have any questions?
Yeah.
Yeah, what do you got, Andy?
For the top ones, did
Yeah.
you used the LN, didn't you?
No, actually I didn't. Hold on. I went ahead and rewrote this to be x to the 1/5 power, whose derivative needs just the good old-fashioned power rule, where you would bring down a 1/5 x to the -4/5, which is the same thing as 1/5. Negative just says pop it down. But remember, 4/5 brings in a radical. Do you see it?
Yeah.
Good. Yeah. It's good that you're thinking ln. You're like 1/u. Well, that's one way to get a fraction, but another way is a power rule, where you get a negative exponent. That's another way to get a fraction.
Yeah.
And the AP loves to have those be answers, because they're good to begin with. There's no denominator, but a derivative has a denominator. Ooh, it's not differentiable. Might be continuous, but it's not differentiable. And you guys know that negatives to odd roots, those are good, right? So all the negative numbers to an odd root is good. This one is an even root. It's a square root. Negatives would be imaginary, but it has +1. So all these -1/2, -0.9s, that would still be a positive number under the square root. That's why I say continuous. This guy doesn't work at 3, but in between -1 to 1, he's continuous. This guy doesn't work outside -1 to 1. These are all things that you guys might have forgotten. His domain. Arc cosine says, I only have values between -1 to 1. This guy says, I don't want +3. Sorry, there's a vertical asymptote there. But this guy, his domain is all real numbers because he's an odd root. And this guy says, I need x greater than -1. Greater than or equal to. Sorry, the square root of 0 is still 0. So that's why he was continuous from here and above. That's good. He's continuous up to 1, but not up to 3. That's good. He's continuous on that exact same interval. And he's continuous for all real numbers. Josh?
Oh yeah, I was just gonna ask if it was still from -1 on B, you could still say, I'm not the right word, but because there can be a square root of a 0.
Yeah, good. But that's why it doesn't exist at the square root of 0, right? So, like, the square root of 0 is 0, but if it's in the denominator, it's a no-go. But that was an endpoint.
Okay.
But yeah, square root of 0 is 0 because 0 squared, 0 times 0 is 0. Okay, that brings us to the end of section 3.2. So then the other section that you guys were supposed to be working on over break was 3.3. I didn't have a Jamboard up because I did have a video up. I do believe I can look at that real fast. 3.3 is this guy. And the directions literally said, watch the following class from last year, which covers notes for 3.3 that they all need to take before moving on to homework, which is below. And this is the homework that was not on WebAssign. Why was it not on WebAssign? We had this whole discussion before break. People that worked on it a lot, why was it not on WebAssign?
Did he get the simplified?
Because I can give you the simplified derivatives if I use the textbook because I know what those functions are. On WebAssign, I don't know what they're actually going to give you until they assign it. And then I'd have to go through and find all the derivatives. I'm like, I have all the simplified derivatives. Now, why is it nice in 3.3 to be able to open this document and know the simplified derivatives?
Take the derivative, go from there.
Yeah, taking the derivative is gnarly. Now, should you have just come here and stolen a derivative? No. You could have done that in an online derivative calculator. But my guys that came in here yesterday being like, what was number 11 one of the hard ones? It was, right? It was a product rule, and then you had to do some simplifying. To get to the simplified derivative, you had to do some common denominator work. Some of the guys that were in here, they made some mistakes on this one. But they knew what the right answer was supposed to be, so they could come in here and they could finish the problem if they knew the derivative simplified and if they knew the critical numbers that came out of setting the top equal to 0. But then they were like, able to come ask me, but how was I supposed to actually get this derivative itself? So all of these simplified derivatives were because taking the derivative can get messy and tricky, and I didn't want you guys to be like, I don't know what the derivative is and not be able to keep going. But hold on. What does 3.3 keeping going look like? What are you guys talking about in 3.3? You're analyzing with derivatives alone. You're analyzing with derivatives alone where a function is going down and where a function is going up, where it's falling and where it's rising. And you do all of that with the first derivative, and once you can figure out where it's falling and where it's rising, we can also figure out then where all the relative minima are and all the relative maxima are, because the minima will always occur between decreasing to increasing. Maxima will always occur from increasing to decreasing. And so this whole idea was kind of fleshed out in graphs, and when you guys, as you guys watch the video, I think these are snapshots exactly from those notes that I did last year. Talking about movement and behavior, not just seeing this as a boring picture, but actually seeing something along or moving along, movement happening within the graph itself. Changes can happen from decreasing to increasing at like D and E, sharp points, or at smooth, even if they're quick, but smooth turns. These are critical numbers, right? Sharp points and horizontal tangent lines. We already know how to find critical numbers, but I could also have changes. Now this one doesn't, but I could have changes happening at vertical asymptotes. And so we talked, first of all, about quickly reviewing how to do increasing, decreasing. This is pre-cal, how to do it with interval notation. But then we say, what if you don't have a graph? And if you don't have a graph, where something that's not strictly going up or strictly going down, where will it change? It'll either change at a smooth turn, that's a horizontal tangent line. It'll change at a sharp turn, that's a DNE, an undefined, a sharp point, or it could change at a discontinuity. All of that was leading us up to, okay, so what? So then, if we are going to be figuring out increasing or decreasing, we need to be plugging in, finding where the derivative is positive, because if the tangent line is positive, my function's going up. My derivative is negative, the function's going down. If my derivative is 0, it's either a momentary stop or it's an actual going constant stop. There's a few different ways that can happen. The increasing, decreasing test just says, how do I know increasing or decreasing? How do I know if it's movement up or movement down? It's all what the tangent line tells you. But how do I actually analyze it is this page. And all of this is going to look very familiar in section 3.4, because 3.4 says, hey, guess what? We're going to be looking at concavity now. Not whether something is just going down or going up, but is it going down in a slowing down way? Is it going up in a speeding up way? Wait, did you guys just hear that? Is it going down in a, actually, yeah. Is it going down in a slowing down way, or is it going up in a speeding up way? All has to do with negative tangent lines going to 0. That means technically the velocity or the speed is going closer and closer to 0. Or the speed is getting higher and higher. Or is it going up in a slowing down way, getting closer and closer to 0? Or is it going up in a slowing down way or going down in a speeding up way? So this one is talking about what are the tangent lines doing. Concavity is what are the tangent lines doing, which starts to get kind of confusing because each of them had a speeding up, slowing down. That's why speed and velocity are different. We'll talk a little bit more about that when we talk about what's going on. But what I wanted you to see was it's important for you to do 3.3 I'm talking to those of you that did not watch the video and did not take notes. It's crucial not only for what's going on in 3.3, but also check it. This increasing or decreasing test, knowing the signs of the first derivative, will be perfectly modeled when we finish this section on Thursday in the concavity test, with looking at the second derivative's signs. And this whole process of analyzing and knowing whether something is increasing or decreasing with what we call a sign chart. This whole process of knowing whether something is increasing or decreasing with a sign chart is going to be basically perfectly copied, just not with the first derivative, but with the second derivative when we do analysis for concavity. They are so similar. Just one's looking at the first derivative, one's looking at the second derivative. So let's go back to increasing, decreasing, if it's so important to kind of get this process down. So to analyze increasing and decreasing, recapping from the video, if changes can happen at discontinuities, we have to start with domain and say, okay, fine, so what are the discontinuities? If a vertical asymptote can make things change, okay, cool, so we got to think about those. Then we have to think about critical numbers, but we can't think about critical numbers until we take a what? Critical numbers come from what? Setting who equal to 0 or DNE? Derivative. So I have to actually find the derivative. So once again, why was this so important to have? So you can have the derivatives. Now, could you just go steal it based on how I did it? I mean, you could. I'm not saying you should. There's a huge lack of integrity there and a weakening of skills. But to practice this process, you need a derivative. You need it simplified because you need to set the top and bottom equal to 0 to get those critical numbers. It's from the textbook, which is online. You can hit the online textbook in WebAssign. It's not in WebAssign itself. It's in the online textbook. You can take pictures of my textbook if you don't know where to find yours, which is a whole other $200 issue for us to deal with later. But coming back here, I do have the derivatives all worked out. Once again, WebAssign does have the online textbook, but you're taking this directly from the textbook so that you can check those derivatives. Once you have those derivatives, nicely simplified, once you've found your critical numbers, you make what we call a sign chart. And a sign chart, a lot of different people do it a lot of different ways. Some people have you make this huge table, which is good, and it does make sure you know what you're doing. It just takes time. So what I try to have you do is try to just think about like a number line. Try to think about something like the x-axis. Now, if your domain is restricted, maybe you stop at something like -4 to 4, and maybe you don't go forever because the domain is not all real numbers. Maybe sometimes your number line is not going forever right, forever left because your domain is restricted. However, other times your domain is all real numbers, so we think about the whole number line. You take any critical numbers that you had, like a C1, like a C2, however many you had, I don't even know. And based on IVT, basically, the only time my function will change from going up to going down is at a critical number. So therefore, all I need to do is test one point in each interval by plugging into the first derivative. If I can plug in 1 point in each interval and know whether the first derivative is positive or whether it's negative, it will speak for the whole interval. All I need is 1, as long as I've portioned it up, using, once again, any discontinuities and any critical numbers. So let's pretend one of these was a discontinuity. Let's pretend something like this is a vertical asymptote instead. So this could be a critical number, and this could be some sort of like VA. So put in any discontinuities as well. As long as I've included any discontinuities and any critical numbers, all I have to do is pick one, plug in 1. Something here on the number line, plug it into the derivative, see if it's positive or negative. Let's say it was maybe like a positive, positive, negative, positive, something like that. Then I know what's happening for all these x values. I know this function must be going up if all the tangent lines are positive. It's still going up, even if it does like a leveling off sort of thing. It still keeps going up because of that test point being a positive. Somehow, after the vertical asymptote, for some reason it's going down, and then it changes to going up. And then I can take from this quick little analysis of, now it's not, the whole process isn't quick. You have to find a derivative, make it simplified, put into a number line any critical numbers, any discontinuities. You have to pick a test point for each interval to say, what sign are you, positive or negative? Nice thing is I don't need to know the number at all. I just need to know positive or negative, which will indicate what my function is doing, how it's behaving. Then I can do things like, well, there was no maximum here. It was going up and then it leveled off and it kept going up. So there's no max there. Ooh, there's a minimum here. It was going down, it levels off, and then it goes up. Whether it was a sharp turn or whether it was a smooth turn, there's a minimum right there at C2. And then I could say, oh, there's a max. Nope. It's a vertical asymptote, so it must have gone up forever and then it must have come from down forever. No maximum there. I know so much about my graph, and that's where the section ends. Because the section ends, I take derivatives, I show you the sign charts. That's why the video was so important to watch. But the first derivative test just takes what we've done with increasing, decreasing, and says, hey, whenever you see this at a crit, there's a min. Whenever you see this at a crit, there's a max. But if there is no change, or if this is happening at a discontinuity, it's neither. And so it says, watch out for discontinuities as well. At some point, kiddos, at some point in the video, this was from the actual PDF, so maybe I didn't get all the other things in there. Hold on. Let's go check it really fast. I made sure I think I had most of these things illustrated. I walked through a lot of these things that we talked about. We were filling in. I was talking about the process. I was talking about the homework being from the textbook. I did some examples. I did some more examples. Then I think the pages that were left blank, I kind of just said, like, hey, if you need more practice, let me know. If you guys do want to see those ones worked out, if you want extra practice, you can fill me in and I can get you videos from a couple years ago as to when I did do more of those. Let me get rid of the simplified derivatives. Let me get rid of the video that you were supposed to watch. And let me, with the last few minutes of class, try to reward those of you guys that came in with homework questions. On section 3.2, this one is supposed to be due by 11:59 because MVT was actually something that we were covering before break. However, I didn't realize that I didn't give you guys a video for it. So I am going ahead and making this one due Thursday at 8 a.m. Well, no, let's just make it 3:30. However, some of you, this is extremely enabling, which is not usually a healthy thing to do. If you use this grace wrongly, if you guys notice on Google Classroom, I have changed the deadline for 3.3 and I'm about to change 3.2 both to Thursday. Because some of you, like Hovan said, like, wait, there wasn't a video. You might not have gotten good examples. So I'm going to go ahead and make 3.2 due by 3:30 on Thursday. I'm going to make 3.3 due by 11:59 on Thursday. And why? Because I just adjusted the lesson plans as you guys were on the boards working. We were going to do 3.4 here and 3.5 there. I have decided to make 3.5 something that we do to recap everything after Christmas break. Now pause. That means we still need to make sure we have a working knowledge of 3.3 and 3.4 by the end of this week. And there is one other important section that seems really weird, but it would be really helpful for the final exam, called L'Hopital's rule. From chapter 7, ask a BC kid why Miss D is making sure for us to cover L'Hopital's. But let me just give you this one word, 2-word summary of it. Limits, simpler. Limits are going to come back on the final exam based on what you've done with derivatives. If you can do limits, simpler, technically it should be 3 words. Tricky limits, simpler. That might be something helpful to put into your tool belt before we review for the final. So, we are finishing 3.1, 3.2, 3.3, 3.4. I have shown you the beginning of 3.4 and I said it's like 3.3. Some of you, by choice, or maybe by ignorance, hold on. Some of you, by choice or by ignorance, have to watch a movie or should be watching the recording of 3.3. If you guys noticed, those of you guys that watched it, it was not an hour and a half, right? There's no way it was an hour and a half. How long was it?
That was 40.
Like 40 minutes? Okay, it was almost... Time out. But you guys need to get those notes on 3.3 because otherwise this whole process in 3.4 and thus half of chapter 3 and thus a huge category of applications of differentiation will be lost on you. And that would be a horrendous move for you guys to make in this class. So one more time. You guys see what's going? Oh, wait. Has anybody seen Friday?
Gosh.
Friday's a minimum day, and I have right now a test. So hold on. Because of what we're doing and because of the section we're taking out, this is going to change into a quiz. I'm going to call it a quest. But can it be very long? Can it be very long if it's on a minimum day?
No.
2 questions.
1.5.
You might just want one. You might just want one.
0.
But as
Negative.
do you need 0?
Optional extra
It's
It's an optional question.
Pause. But our goal is to finish 3.1 to 3.4 before Friday. We'll talk more about the quiz, the quest on Friday itself. Sarah, I see that question. As you ask it, let me get back in, making sure I've made the change real fast, because otherwise things are going to be sad.
Yeah, I was just gonna ask, so nothing's due tonight, right? It's all due Thursday?
Well, for some of you, what's due tonight is, I'd say, watching the 3-3 video and getting
Right,
notes.
but like,
Does that make sense?
assignment?
But assignments, deadlines-wise, no.
Okay, thank you.
Yeah. For those of you guys that did put in the work on section 3.2, maybe we should not show everyone this for a second. Ooh, so many 100% and then so many missings. Okay, so on section 3.2, was there any place that you guys wanted me to go for those of you that did attempt NVT? 12. Cool. On number 12, they give you a good old-fashioned, which for me is old-fashioned, for some of you is still very, very new. For physics, it should be somewhat old-fashioned as well. It gives you a position function. Pause. I know some of you are like, I'm behind, but pause. We all reviewed NVT at the beginning of class, went to the board, sat down, and were able to do some work on NVT. Why am I bringing that up? Because all of us can tackle this problem. Why? It gives me position, and it asks me for average velocity. Isn't average velocity the same thing as average rate? Isn't average rate like the f of b minus f of a all over b minus a, except this guy's not named f? Isn't he named s? So shouldn't we just be the first 3 seconds? Isn't that the 3rd second minus the 0th second?
Yes.
So I can go ahead and use what you did at the beginning of class by plugging and chugging. It's going to be a decimal, plug it into your calculator, no big deal, yeah? But why does the second piece say, okay, now do NVT? Well, what would NVT have me do? We take the average. What else do we do? Take the derivative. So I would do the derivative, and what does NVT have me do after I do a derivative? I take the 2, and what do I do?
Make them equal.
I make them equal, and I plug in a c, right? Ultimately, I can already peek and see what that is, so therefore it's going to be negative 14.7 after all of that work. Shouldn't we be able to solve for c?
Yes.
And shouldn't it end up falling somewhere between 0 to 3? No, NVT today. I hope so. Get out of here. Some of your goals are to finish 3-2 and watch 3-3. I'll see you guys later. Hopefully that was productive. If I can help you in any other way, you know where to find me. If I'm not here, I'm at the senior board outside supervising. Bye, guys.
The only good win is against Notre Dame and Notre Dame.